Hi everyone, this is lesson 1-2, analyzing graphs of functions and relations. Our learning target today will be for students to be able to identify different types of symmetry in graphs of functions. Here we have key concept number 1, and it discusses the test for symmetry. We have a graphical test. The graphical test listed here states that the graph of a relation is symmetric with respect to the x-axis if and only if for every point x, y on the graph, the point x negative y is also on the graph. So what they're stating here is they give you a model or an example of what the graph might look like that has x-axis symmetry. And what you see here is you have an ordered pair x, y in the first quadrant. And it doesn't have, that point doesn't have to be in the first quadrant, but you just have an ordered pair, and what you want to see is that another point on the graph has the exact same x value but opposite y values. So for instance, if this point here was 1, 4, what they're saying is if the function has x-axis symmetry, the point 1, -4 has to be on the graph as well. So I'm providing some numbers here just to give you an example instead of being so general with the x and y coordinates. I'm trying to provide some numeric values there to help you understand that the same x value has to give you opposite y values for a function or a relation. Obviously, this is not a function. That's kind of a mistake on my part. This would not pass the vertical line test. That is why they use the word relation. A relation is just a set of ordered pairs, but it's not necessarily a function because not all relations pass the vertical line test. So, referring back to the definition of what a function has to pass the vertical line test. Any graph that has x-axis symmetry is not going to be a function. Algebraically, we would replace y with negative y, and it produces an equivalent equation. I'm not so much going to focus on the algebraic test when we are doing the examples. I'm more going to focus on these numeric values here, providing a table of values to determine whether the relation or graph is a function. Now, moving on to a new type of symmetry, we have symmetry with respect to the y-axis. The graph of a relation is symmetric with respect to the y-axis if and only if for every point x, y on the graph, the point -x, y is also on the graph. So notice that for these two ordered pairs, when you have y-axis symmetry, again, here's our y-axis. If we folded our paper along that line, we would have two equal or mirror images, and what we have here is opposite x values that produce the exact same y coordinate. So our x coordinates are opposites of one another, but our y coordinates are the same. So if we had this point again, just to give some numeric values to this example, we would have 1, 4 in the first quadrant. Then -1, +4 would also have to be on the graph if the graph had symmetry with respect to the y-axis. Again, I'm not going to really so much focus on the algebraic test, but replacing x with -x in the equation would produce the same or equivalent equation. The graph of a relation is symmetric with respect to the origin if and only if for every point x, y on the graph, the point -x, y is also on the graph. Okay, we have positive x, positive y here, and we have -x, y. So what we're saying with origin symmetry, if the point 1, 4 is on the graph, then -1, -4 would also have to be on the graph. So what we would say is for opposite x values that are opposites of one another, the y values that are paired with those x values are also opposites of one another. So 1 and -1 are opposites, just like -4 and +4 are opposites of one another. Algebraically, if we were going to show algebraically origin symmetry, replacing x with -x and y with -y would produce an exact same equivalent equation. In example 5, we're going to test for symmetry. And in part A, we're going to use the graph of the equation y equals x squared plus 2 to test for symmetry with respect to the x-axis and the y-axis and the origin. And we're going to support the answer numerically with a table of values. And this is going to be enough for me. I don't expect you to do the confirmation algebraically. So what I want you to do is go ahead and graph this function y equals x squared plus 2. On your graphing calculator, you can type in y1 in your equation editor, x squared plus 2. And then you can go to the zoom menu and choose option number 6, which is z standard. I'm going to abbreviate standard here. And that will give you a picture that is very similar to this. And we don't have a standard window on this particular graph, but on your graphing calculator you can use a standard window. And what I need to do is then go to the table setup, which is found by pressing second in window and changing my independent variable to ask. By changing your independent variable to ask, when you go to the table by pressing second and then graph, you will find that you should have a blank table, or if there's numbers in there that you can delete them. And what I'm going to do is I'm going to create a table of values. So what I'm going to do is I'm going to choose some x values that are opposites of one another, because y-axis symmetry is found by taking opposite x values that give you the same y value, and origin symmetry is found by giving me opposite x values that give me opposite y values. Now, here I already know that this graph does not have x-axis symmetry. Clearly I do not fold here and get 2 equal halves. So, but I do think that our graph has y-axis symmetry, vertical, and what I'm going to do is I'm going to pick a couple x values that are opposite, so like -2 and +2, and I'm going to evaluate the function right here, and plug these, first of all, plug these values into my table, and if you do so, you should get 6 here and 6 here. At -2, if you plug -2 into your table, you should get 6, because 2 squared is 4, 4 plus 2 is 6, and if you plug in +2 for x, you get 2 squared, which is 4, and plus 2 is going to give you 6. So when you are looking at this table, I'm going to just check another pair of opposite x values to make sure that's not too good to be true. But I'm thinking, since I got the same y values here, that we have y-axis symmetry. If I plug in -3 for x, I would get 11 for y. And if I plug in +3 for x, I would also get 11 for y, which then confirms that we have y-axis symmetry, because we have opposite x values here that are giving us the exact same y value. So here we have a pair of opposite x values that are giving us the exact same output or y value. So that is a numerical confirmation that we have y-axis symmetry, which we also can see from the graph. Example 5, part B, we're going to test for symmetry. Use the graph of the equation x times y equals -6 to test for symmetry with respect to the x-axis, the y-axis, and the origin. And we're going to support the answer numerically with a table of values. Like in the previous example, I do not expect you to do the algebraic confirmation. And what I would start by doing is solving this equation here for y. So x times y equals -6. And if I divide both sides by x, because I'm multiplying x and y, I would get y equals -6 divided by x. And if I graph this on my equation editor, on my graphing calculator, I should get this graph. And I can go ahead and graph this function on a standard window. So you could use Zoom option number 6, which is Z standard. And to do that, where I go from there is I'm going to go to my table of values. And hopefully your table settings are on ask for the independent variable. And I'm going to pick a couple different pairs of opposite x values. So I'm going to do -1 and +1 and 3 and -3. And I'm going to fill in the y column of my table. So if I plug in 3 for x, -6 divided by 3 is -2. If I plug in -3, -6 divided by -3 is +2. And if I plug in -1 for x, I get +6. And if I plug in +1, I get -6. Now, what I'm going to do here is look at my table of values. Since I have a pair of opposite x values that give me y values that are opposite, and same with -1 and +1, they're opposite x values. Y values at 6 and -6 are also opposite. That makes the graph have origin symmetry, which means that if I folded along this line here, or if I reflected every point on this piece of the graph across the origin, if I reflect this point here across the origin, right here, it's going to land right here, and so on. This point would reflect down here, and this point would reflect over here somewhere. So what we have is a demonstration of a graph that has origin symmetry. We've confirmed it numerically by showing that opposite x values are paired with opposite y values, and therefore we have origin symmetry. In example 5, check for understanding. We're going to use the graph of the equation y equals -x cubed to test for symmetry with respect to the x-axis, the y-axis, and the origin, and support the answer numerically. Then confirm algebraically. So we have 4 choices here. We're given the function f of x equals -x cubed. If you graph it on your graphing calculator on a standard window, you should end up with a graph similar to the one drawn here. And what you want to do is determine the type of symmetry this function has, and we can go ahead and just support it numerically. You just provide a table of values. You do not need to confirm it algebraically. And you have 4 choices, A, B, C, or D. Work out the problem and then press submit when you have found your answer.